Welcome to ePG Pathshala, lectures on numerical methods. This is a module on interpolation with equally spaced nodes. This is second module in that on that topic. In the first topic, we already considered the derivation of the formula for Newton's forward difference interpolation polynomial and Newton's backward difference interpolation polynomial, and we have seen some illustrations and comparison of the estimates obtained by both these polynomials in the previous module. In this module, we are going to talk about algorithms for Newton's forward difference interpolation polynomial and Newton's backward difference interpolation polynomial. We will study its time complexity and we will carry out the error analysis for both these interpolating polynomials. So, in this module algorithms, this and their time complexities will be discussed. Also, the interpolating error for those formula will be computed and analysis of factors contributing to these errors will be discussed. So, we first consider the algorithm for Newton forward difference interpolation polynomial. As usual, we are saying that when we are talking about algorithm, we talk about what are the inputs to the algorithm, what is the output to the algorithm, and then the iterative steps. So, input to this algorithm will be data points x I, y I for I equal to 1 to 3 up to n, and such that we ensure that these data points are equally spaced, because these formulas are applied only for equally spaced nodes. With now, the step size here will be given by the difference between any two consecutive x values. So, that is x 1 minus x 0. So, h is my step size. That is also taken as an input, or you can compute it from the data points. And then we are giving the value x at which you want to estimate the value of y, and which is not given in these nodes. So, x is in a b, where a is the smallest value and b is the largest value here, observed value. If true functional relationship between x and y is known in terms of the functions f, then even we can get only n, x 0 and h as input, and we can compute the n plus 1 data points using this kind of for loop. For example, y 0 will be equal to f x 0, and for I equal to 1 to n, we compute x I as x I minus 1 plus h. So, iteratively we generate the arguments, and then you evaluate y I as a function value at x I. So, that we can do. So, provided we know the functional relationship between y and x. The output to the algorithm will be nothing but the nth degree forward difference interpolating polynomial over the given data points and the values of the coefficient a 0, a 1, a 2, a 3, n. So, I am trying to find out, estimate the value of y at x using this p n x, where p n x is the nth degree forward difference interpolating polynomial over the given data points, and values of the coefficients a 0, a 1, a 2, a 3, n. So, that if you want to write that polynomial, then we can use these coefficients, and the algorithm NFDIP is given in terms of what? Now, it is given in, if you remember that in the previous module we have given the concise form of this polynomial, interpolating polynomial, and that is given in terms of the value s, which is computed from x minus x 0 by h. X is the value given as input, x 0 is your first observed point value of x, x minus x 0 at divided by h is the step size. So, that is my s. Then your p x is given in terms of this. So, p x will be nothing but, so in general x will be equal to, from here you can compute x will be equal to h s in plus x 0. So, p x is same as p of x 0 plus h x, and which is given in terms of this. This formula was derived in the previous module. So, f x 0 plus s into delta f x 0 plus s into s minus 1 upon 2 factorial of delta square f x 0 and so on. These are the forward differences. This is first order forward difference, this is second order forward difference, and this is nth order forward difference of f at x 0. Now, if you want to consider now this formula, how to compute this now. So, what I am trying to do is, since we are thinking in terms of computer implementation, I am denoting this delta k f x I as array or 2 dimensional array, which is called forward difference array over k comma I. K is the order of the difference and I is the point x I at which this forward difference is computed. So, for k equal to 1 2 3 up to n, because you want n order differences, and you know that as your order of the difference increases, the number of differences that we compute goes on reducing, and that is given by. So, therefore, k equal to 1 2 3 up to n and I is 0 1 2 3 up to n minus k. So, the first order difference will be there will be n minus n differences of first order, n minus 1 differences of second order, and only one difference of nth order. So, that is how you will compute this f d k I, and these f d k I's are computed iteratively, because by definition you know that there is forward differences can be computed iteratively. So, iteratively as follows. So, what we do is we initialize first for I equal to 0 to n, we are writing f d 0 x I equal to y I. You know that the 0th order difference is nothing but the value of y I actually, and then we are computing. These are all initializations we are trying to do. So, first we are initializing the 0th differences of all order, I mean at all points x I, and then we are saying that a 0, that the first coefficient of the interpolating polynomial, that is given by f d 0 x 0, and your interpolating polynomial value I am initializing its term as a 0. So, we are computing, you know that this polynomial we are given here like this. So, we are working out this value of p x, and this value of p x we are working out with this actually. So, we are considering here that this will be the first term, then you add second term, then you add third term, like that we are doing, and therefore, in the initialization we are taking p x as equal to y 0 or a 0, that is one and the same here, and that is what we are considering. So, you can see here your first value of a 0 is given by p x equal to a 0, because what is a 0? A 0 is f d 0 y 0, which is same as y 0, and y 0 is nothing but f x 0. So, that is how I will get p x equal to a 0 as initial value of p x, and then we go on adding subsequently the new terms. The first, so term is also called computed iteratively, and that term t initialized to 1, and s, as we have already said, that it will be x minus x 0 by h. So, all this initialization is done in this step, and then iterative step will go on adding term by term in the p x value, and then finally we will get the p x value. So, this will be done for k equal to 1 to n, because there are n terms, and for I equal to 0 to n minus k. So, first we are computing these two for loops are computing your forward differences of all order. So, I am considering here f d k I. So, kth order difference at x I, that is what we are computing, that is given by k minus 1th order difference at I plus 1 minus k minus 1 difference of at I. So, that is what we get. This is your iterative formula for forward differences, and once you work out of both these for loops, I will be getting all forward nth order up to nth order forward differences. Now, a k we are considering, you know that when you are using forward difference interpolating polynomial, we are simply using kth order difference at x 0 only, and therefore, I am taking f d k 0 as my coefficient a k. So, all the a k's are going to be given by f d k 0. Now, your term I am computing as t equal to t star into s minus k plus 1 by k. Now, where this comes from, if you look at again, we go back in the previous here, we can see here that this is my term I am computing. This is your forward difference, which is already given as a n or a 1 here, a 0, like that. In general, we will be getting a k, and this term is computed iteratively. So, first I was taking 1 and then you multiply by s. So, I will get second term here, then I will get s into s minus 1. So, that I will get as third term. So, like that these are iteratively computed and we have to divide by factorial. So, this is 2 factorial, this is n factorial and so on so forth. So, therefore, I have to divide by 2. So, that is what I am trying to do when I am computing my p x iteratively like that. So, here this term I am calculating like this. So, term is equal to t star s minus k plus 1 by k. So, this is divided by k. So, if k is equal to 1, I will be getting only s. So, t initial value of t is 1. So, 1 into s. So, this will be s. If I get k equal to 2, then my t will be s and then I will be writing s minus 2 plus 1. So, this will be s minus 1. So, s into s minus 1 by 1 into 2, that is 2 factorial. So, that is how I will go on getting this iterative terms and then you are adding this term p x to p x. So, initial p x was a 0. So, then I will be getting a 1 plus a 1 into s plus a 2 into s into s minus 1 by 2 factorial and like that you go on adding these terms and this is what I will be getting your value of p x. So, my output is now clear that this is p n x, that is I am writing here n only to indicate that this is nth degree polynomial. So, p n x is nothing but p x here. So, this is what I will get as output and the coefficients a 0, a 1, a 2, a 3, a n, which are the coefficients of the Newton's forward difference interpolating polynomial. So, this is my output I get. Similarly, I can now work out on the algorithm for Newton's backward difference interpolating polynomial. Now, you know that in the backward difference interpolating polynomial, we are working out backward differences. So, again we have got input to the algorithm same as the previous one. So, this is n data points x I, y I equal to 1 to 3 up to n and 0 1 to 3 up to n and such that x 0 x 1 x 2 are equally spaced with step size h equal to x 1 minus x 0 and x belonging to a b, where you want to evaluate the value of y and where a is x 0 and b is x n. And output to this algorithm is p n x and the value of the nth degree for backward difference interpolating polynomial over the given data points at x and values of the coefficients which are going given again in terms of a 0, a 1, a 2, a 3 n, but in this case these are going to be different than what we were computing in the forward differences, though the notations used for the coefficients are same. Now, the algorithm starts again with let b d k I. So, I am considering kth order backward difference at point x I is represented by b d k I, where k is equal to 1 to 3 up to n and I is equal to k plus 1 I equal to k plus 1 up to n. So, we are for computing backward differences from back side and we go only up to k. So, k to n. The backward difference interpolating polynomial is given as follows. So, this is given by p x equal to x n plus h s, where what is s here? S is nothing but x minus x n by h. So, this is your x. So, s will be equal to x minus x n by h. So, that s I am computing and then my backward difference interpolating polynomial will be given by this formula. So, here you can see that it is s into s plus 1 up to s plus n minus 1 upon n factorial in the last term. The second term will get s into s plus 1 by 2 factorial and this, and the coefficients are nothing but the backward differences. And these backward differences are evaluated at the last node, that is x n. All right. So, now we will try to write down the algorithm. So, again we will initialize just as we have done it in the earlier case. So, I am writing here first we are computing 0th differences. 0th differences are nothing but the values of y i's. So, I equal to 0 to n b d 0 I will be equal to y I. A 0 will be equal to b d 0 n, because I am taking last node actually. So, the 0th order difference at the nth node. So, that is b d 0 n and p x will be equal to initialized by a 0 first. So, first term and then, or you can call it a 0th term and then you go on adding subsequently the terms like that. and term is initialized by 1. So, t equal to 1 and your s is taken as x minus x n by h. So, these are all initializations done and then we are calculating here iterative step like this. So, for k equal to 1 to n, for I equal to k to n, we are all calculating this backward differences k to n. So, I am getting b d k I will be equal to b d k minus 1 I minus b d k minus 1 I minus 1. So, like that I am going to compute the backward differences like this. So, when k is equal to 1, I will be computing differences from 1 to n, k equal to 2, I will be computing from 2 to n, like that we will be doing. And you can see here a k, I am going to write it as backward difference at x k and at x n, a kth order backward difference at x n, that is my a k. And t again, now here I am going to take it as s plus k minus 1, because I want s into s plus 1, s plus 2 like that. So, therefore, term will be taken like this and you divide by k, because k factorial is anyway required in the denominator, and then p x will be equal to p x into a k star t. So, that will term by term we are adding, and when this for loop is over, automatically everything will be computed. So, this will be done here and then we are considering this for loop. So, when this for loop finally gets over, I get everything and I will get a value of p x. So, naturally output will be p n x is equal to p x and coefficients are again a 0, a 1, a 2, a 3, a n will also be given as an output. So, this is backward difference. Both these algorithms are fairly similar to each other, except that one starts with x 0, I mean you are using forward differences at x 0, here we are using backward differences at x n, and similar computations are done in both the cases. Now, we compute the time complexity, and because both the algorithms are similar, time complexities will also be just the same, and therefore, I am going to do both this together. So, the algorithms Newton's forward difference interpolating polynomial and Newton's backward difference interpolating polynomial computes n into n plus 1 by 2 forward difference or backward differences. Why? Because we are using here this one backward difference like this. So, 0th order backward difference is n times done, first order backward difference is done n minus 1 times, and so on and so forth, n times it is done, and like that we will be doing. So, k equal to 1 to n. So, n first order backward differences, n minus 1 second order backward differences, and like that we will be getting nth order. So, therefore, we will be getting total backward differences computed will be n plus n minus 1 plus n minus 2, and like that. In forward case, it will be 1 plus again same n plus n minus 1 up to n. So, up to last difference will be 1. So, like that we will be getting n into n plus 1 forward or backward differences are computed, and each one of them require one subtraction, because this is just the difference, right, just the difference of the two k minus 1th order backward differences, and therefore, it will require only one subtraction operation. You know that time complexity is computed in terms of arithmetic operations, or they are called flops, actually floating point operations required for computing the algorithm. So, we will get here one subtraction operation here we required. In addition, one subtraction and one division is required to compute s, because s is nothing but you have got s is what x minus x n by h. So, one subtraction, one division. So, we will get that multiplication, and in addition are required to compute p n x. So, these are for s, and then 3 n multiplications and n additions are required to compute p n x. Why 3 n multiplications? Because in each term we are multiplying there. So, you can see the algorithm and you will realize that how many multiplications are required. One multiplication required here in each iteration, one division, that is also same as multiplication operation, and here one multiplication. So, 3 n multiplications and one addition operation we are doing here. So, 3 n multiplications and n additions we are considering, because in each loop I will be doing one addition. So, n times when the loop is evaluated or executed, you get n additions. So, we will get 3 n multiplications and n additions are required to compute p n x. So, hence the time complexity will now become what? So, 3 n plus 1 into m plus n square plus 3 n into a by 2. How do you add? You add all this. So, we add this many forward differences we are computing, and for each of them there is one addition operation. So, this into a plus 1 subtraction and in addition 1 subtraction and 1 division operation required. So, one more a here, okay, one more addition here, and then one more multiplication are required from here, then 3 n multiplication. So, 3 n plus 1 multiplications will be required anyway. So, total 3 n plus 1 multiplications, and these additions we are adding, when you add you will get n square plus 3 n into a by 2. So, these many addition operations will be required. So, thus the asymptotic time complexity, if you look at, you know that asymptotic time complexity is computed in terms of the size of the problem, that is n here in terms of n, and the highest power of n is considered as asymptotic complexity. So, highest power of n involved in this expression is n square, and therefore, asymptotic time complexity is given by order n square. That means, the time required for the algorithm as n increases, it is similar to increase in n square. So, it will be increasing like this. That is my asymptotic time complexity, and note that the number of multiplication operations are significantly reduced as compared to Newton's divided difference interpolating polynomial algorithm. If you compare the multiplication operations required in the Newton's divided difference interpolating algorithm, that will be much more as compared to this, and that you can verify from your previous modules. Now, we come to the error analysis. So, formula for error E x in estimating a function value at some point x in the domain of observation by Newton's forward and backward difference interpolating polynomials can be computed from error formula for Newton's divided difference interpolating polynomial, because all these are nothing but derived from Newton's divided difference interpolating polynomial, and therefore, the same error formula we can do it, except that we will have to replace something. So, Newton's divided difference interpolating polynomial by replacing the divided differences by forward or backward differences respectively. So, this is what I have to do. So, now you remember that this is what we had done. So, since forward difference interpolating polynomials is derived from Newton's divided difference interpolating polynomial, over the nodes this, the error x E x is given by E x equal to f n plus 1 z x. Z x is some point in the open interval a b, n plus 1 factorial here into x minus x 0, x minus x 1 into x minus x n. And now, if I want to write in terms of s, I am writing in terms of s, you know that x minus x 0 by h is my s, and this will be s minus 1 by h, and so on and so forth. So, I will be getting all these factors will be divided by h. So, I get h raised to n plus 1 here. When I am writing x minus x 0, I will write h into s, h into this, h into this. So, h will come in n plus 1 times. So, therefore, this I will be getting h into h raised to n plus 1 into this will be replaced by s, this will be replaced by s minus 1, this will be replaced by s minus n, and so on. So, therefore, your error term will be given by this, where s is nothing but x minus x 0 by h, which is computed, which is given in forward difference interpolating polynomial. So, error in terms of s and h we can compute like this. This formula helps us to get the bounds on the error E x on some domain. However, in order to analyze the factors contributing to this error, some numerical experiments will have to be performed. So, what I am trying to understand is, if now obviously that we are approximating the original functional relationship, and therefore, there has to be some error in estimate of y at x, and this error we want to analyze and we want to find out what are the factors which are contributing to this error. These factors we are trying to find out, and in order to know these factors, what I am going to do is I am going to perform certain experiments here. So, I am going to get 3 illustrations, and which are chosen specifically with some purpose, and the 3 functions have been selected which are approximated by interpolating polynomials of various degrees. So, polynomial degree also we are varying using Newton's forward and backward differences formula, and their plots are compared with the plot of the original function. So, we may have original function in mind, because in order to have actual error and then you can find actual value and the estimated value, then only we can get the error, and therefore, I am selecting the illustration such that where the functional relationship is predetermined given already. So, these functions selected are like this: f 1 x is taken as 1 upon 1 plus x square, f 2 x is taken as mod x minus 0.5 into mod x minus 1.5, and f 3 x is selected as e raised to 2 x into cos 3 x. If you remember, such a function was also considered in earlier modules, and even this Runge's example was also considered, because this is these are all very typical test functions for testing your errors. The function f 1 is known in the literature as Runge's counter example, which is such that an interpolating polynomial of degree, howsoever large, will not agree with the true function value at some points x in any interpolating interval. So, this example is such, and therefore, it is a specific example we are considering here, and this can be observed in the literature, you can find out from there. So, we are saying that this Runge's counter example is such that an interpolating polynomial of degree howsoever large will not agree with the true function value at some points x in any interpolating interval. So, we will always get significant errors at some points in the interval. Note that f 1 0 is 1 and f 1 x is smooth and tends to 0 asymptotically as mod x tends to infinity. You can see here f 1 x, when I put 0 here, I will be getting 1. So, your function will be decreasing from 1 to asymptotically it will decrease to 0 as x tends to infinity. On both the sides we will get that. The function f 2 x is continuous. I am just describing the characteristics of this function selected. Continuous, but non-smooth. So, I am trying to consider a function which is not differentiable at points 0.5 and 1.5. You can select any 2 arbitrary points actually. You may take 1 and 2 or anything of that sort. So, I will take 0.5, 1.5 here, and the function f 3 is smooth function, totally smooth, everywhere it is differentiable and all that is satisfied. In fact, infinitely differentiable function, which is same as in example 1, earlier example 1. So, that is how we are considering this. Now, a MATLAB program has been developed to compute this algorithms we have already written. On the basis of that, we can develop a MATLAB program on that, and has been developed to compute Newton's forward and backward difference interpolating polynomial, compare their plots with that of original function plot, and thereby carry out error analysis. This is my intention. Okay. So, as a first experiment, the function f 1 x 1 upon 1 plus x square is approximated by Newton's forward and backward difference interpolating polynomials of degree 5, 10 and 20. I want to do it because I want to see that whether my approximation depends on the degree of the polynomial or not, that I want to find out. And we are doing it on the interval minus 5 to 5, because I want a small interval where I can do the test and draw the graphs and check the figures to find out what are the errors and all that. So, I am giving 3 figures, 1a, 1b, 1c depicts the comparison of the graphs of the function f 1 x with respectively with 2 interpolating polynomials of degree 5, 10 and 20. So, on the interval minus 5 to 5. Now, because the error at the end points is so large that I am not getting clear picture, I am truncating this interval slightly and repeating the third 1C graph in 1D. So, I am just restricting my attention only on interval minus 4.5 to plus 4.5 and trying to get this idea as to what happens in that interval. So, you can see here that the original curve is given in blue, Newton's forward is given in red, and Newton's backward is given in black. You can see that there is no red curve seen in the graph. It's and we verified that it's actually merges with black, and therefore, only black curve is seen here, red curve is merged with the black, and therefore, both these Newton's forward or backward difference interpolating polynomials are exactly same. So, this is minus 5 to plus 5. So, this is your original function which is given in blue. So, original function starts like this. You can see here this goes like this, and you can see that if it is degree 5, this is degree 5, and therefore, I am getting now a lot of error. You can see here there is a lot of error here, lot of error here, everywhere there is an error we are getting. Similarly, if you now take degree 10, so you can see here that graph original graph is again the same, minus 5 to plus 5 we are considering, but you can see now there is a bit better matching in the central places, whereas here the error increases on the towards the end. And the same thing you can observe with polynomial of degree 20. You can see here polynomial degree 20 in the middle case, it is very close, and the error at the end becomes very large error we get here. We are getting very large error on both the sides. So, what is happening here is that these errors are increasing in the end, and therefore, we truncate this interval and try to look at what is happening here. So, if I truncate it by 0.5 on this side and 0.5 on the other side. So, that graph when I look at little in the smaller interval, I am getting better picture here. You can see now that blue curve almost coincides up to this, and then your error is coming. So, the small error, then little big error, and then again it goes bigger, and if you see it goes like this. So, therefore, there is the error goes on increasing towards the end, you can see that. So, this is about first f 1 x, this is f 2 x now. So, this function is absolute value of x minus 0.5 and absolute value of x minus 1.5. You can see that original graph in that case will give me peaks at these points. Original graph will be like this, and you know that it is not going to be differentiable here. So, does that differentiability affect my estimates or not, that is what I want to check. And you can see that the original curve is like this. Again here black and red curves are overlapping, and therefore, Newton's forward or backward estimates are identical. There is large error, this is 5th degree polynomial, we are considering, and then we are considering there is a large error here, large error here, there is some slight agreement, but there is still some error shown here, and like that we will be getting. So, the estimate is not really good. Now, if you take 10th degree polynomial, then you can see that error is there here large, here at the point of non-smooth peak at this corner points, there is some error, bigger error you are getting here and here, but there is a good agreement here, better agreement here, and there is some agreement on this side. So, you can see that the function and its estimates agree in the center place away from the corner points, like that we can check. Then again you can get here the similar situation, again large error towards the end, and we are getting a big function. The original function will be like this, and then if you truncate this, I will be getting your values like this. So, your original function you can see both and this are quite matching in the central place, but again towards the end it goes on changing. So, this blue is original, black and red are away from this. So, towards the end you get always some error in this function 2. When I am considering the function 3 as the third illustration, the function f 3x is given by e raised to 2x into cos 3x. You can see that this function will go on tending to, I mean, as x increases, e raised to 2x will go on increasing to infinity, and cos 3x will oscillate between -1 and 1, and therefore, the function value will also oscillate to minus infinity to plus infinity, like that it will go on doing this. Newton's forward and backward difference interpolating polynomial of degree. Now, here I am taking degree 4, 8 and 16 over the interval -2 to 2. I am taking smaller interval because e raised to these values will rise very fast, and therefore, I am taking interval smaller interval here. Again I am doing the same thing, 3a, 3b, 3c, depict the comparison of the graph of the function f 1 x respectively with two interpolating polynomials of degree 4, 8 and 6, actually f 3 x, not f 1 x. This is f 3 x respectively with two interpolating polynomials of degree 4, 8 and 16, and the figure 3d shows the plot of figure 3c on the truncated interval -1.9 to 1.9, because we thought that is that phenomena which is giving large error towards the end exists for this particular function also or not. And you can see that the observation is like this. This is your blue curve, and now you can see the black curve. Everywhere there is an error. At very few points it agrees exactly, but there is an error everywhere. This 5th degree polynomial, 4th degree polynomial. Now, we are taking 8th degree polynomial, and you can see that there is a bigger match. I mean, like only here you see some error. Again, Newton forward backward are both identical only. There is no red curve seen anywhere, and the black curve overlaps red curve, and there is some error here on this side. There is a good agreement here, and there is some error on this side. So, agreement is better with 8th degree polynomial, and with 16th degree polynomial almost they are coinciding the whole thing, and it was not required even, but still we take 1.9 to -1.9 to plus 1.9, and you get the same picture here, because this agreement is on the whole interval, it is also bound to be on the smaller interval too, and you can see that here you get better agreement. Now, this figure 3d, and now we can do the analysis. In all the 12 cases, the forward and backward difference interpolating polynomials almost coincides. Note that in the MATLAB program, long format has been used, and hence the computational accuracy is up to 15 significant digits. On checking the values of the forward and backward difference interpolating polynomials p and q respectively, it is observed that difference between the estimates by forward and backward difference interpolation formula is approximately of the order 10 raised to -12, and therefore, you can presume that, or you can consider that there is no difference between the two, because this much accuracy is not even required in many of the applications. So, in most of the practical situation, this much accuracy is not required, and therefore, any of the two polynomials can be used for the estimation purpose. So, that means there is no difference between backward and forward as far as estimation is concerned here. So, that is my first observation. In each of the 3 illustrations, the lowest degree polynomial does not give good approximation, and the error E x is significant at almost all x. All the 3 examples illustrate that. So, it is better to go for higher degree polynomial approximation. This is basically due to the large step size, because step size become very large when you are taking polynomial of degree less than 5. So, that means, when you are doing a fixed interval, and if you are integrating, estimating with a lower degree polynomial, So, you are taking only a 5th degree polynomial will require only 6 points, and therefore, your step size become 1/6 of this interval. If I use 20th degree polynomial, the step size will be 1 upon 20, and that is the difference. So, because step size is large, then error is large. This is our second contention. In the first two illustrations, as the degree of the polynomial increases, error E x goes on reducing in the middle of the interval of interpolation, and the length of the interval of agreement goes on increasing. So, in which interval the agreement is there, that interval goes on increasing, but towards the end there is always a problem. However, towards both the ends of the interval of interpolation, the error E x goes on increasing, and this is what happening in the first two illustrations. In the third illustration, as the degree of the polynomial increases, error E x goes on reducing, becomes almost 0 on the entire interval of interpolation. So, that is the important issue here. It depends on the what kind of function you are trying to approximate by these polynomials. So, the above observation lead us to more general implications regarding the convergence of the interpolating polynomials. Let p k x be the sequence of interpolating polynomials of degree k obtained by any of the interpolating formula approximating a function f x, then a given point x in the interval of interpolation except the interpolating nodes, p k x may or may not converge to f x. That is possible, may or may not converge to f x, because you can see that at least towards the end you may get non-convergence. The formula for the functions f 1 x and f 2 x, the sequence p k x converges to f x for the points x away from the end points. P k x converges to f x away from the end point. So, in the middle converges, and it does not converge. In fact, in this case the sequence diverges towards, when you come to towards it, the error goes on increasing in fact. And for the function f 3 x, the sequence p k x converges to f x for all x in the interval. So, you can see that the error depends not only on the degree of the polynomial, or degree of the polynomial depends on step size. So, it depends on the step size, it depends on the where you want to estimate the value, and it also depends on the form of the function to which you are finding out the approximation. So, this is what we can conclude, these are the factors contributing to error. So, in summary, we can see that in this particular module we discussed the two algorithms for Newton's forward difference interpolating polynomial and Newton's backward difference interpolating polynomial. We have studied its time complexity, and we can see came to the conclusion that the asymptotic time complexity for both these algorithms is order n square, and we have given 3 illustrations which will give you the detailed error analysis as to how the interpolating error in both the cases changes. The major conclusion that we draw here is that both the polynomials coincide on almost all the illustrations here and at all the points, and therefore, we have never seen the difference between backward and forward difference interpolating polynomial. Thank you.